So everything else I got. Literally chapter 2. Oh yeah, chapter 2. I did.
Okay, I gotta hustle. So here we go. We're on electrochemistry. So the conversion of chemical to electrical energy, or reverse, is known as electrochemistry. And electrochemical reactions have one thing in common. They involve a transfer of electrons between reactants. Okay. Some major categories of chemical reactions are substances that, or have reactants that transfer electrons between each other. So synthesis and decomposition reactions that have species in elemental form always involve electron transfer. That means if you have something like magnesium plus oxygen is producing magnesium oxide. I realize this isn't balanced, but I'm just giving this as an example. These would be the elemental form of magnesium and oxygen. Does that make sense? Okay. And then if we're talking about single replacement and combustion reactions, those also fall into the category of having electron transfer. Okay. So anytime you've got electron transfer occurring between reactants, it's called an oxidation-reduction reaction. We abbreviate it as redox for short. We good to go? Okay. Let's talk about double replacement reactions. So double replacement reactions do not involve electron transfer. Also, if you've got synthesis and decomposition reactions that have oxides, this is a smaller group. If you do not involve electron transfer, then that means you are a metathesis reaction. Take a look at the next page. Okay. All the rules for determining oxidation numbers are given on this page. I'm going to fill some of them in that are missing. So anytime we're keeping track of oxidation numbers, what we're doing is we are looking at the electrons that have been transferred between elements during a chemical reaction. They sometimes call oxidation numbers oxidation states, or the exact same thing. So these are going to be sort of like these imaginary charges or numbers on atoms or ions when we are looking at things. I'm going to jump straight down into the table. Sound good? Okay. So in the table, yikes, don't go that far. Okay. Anytime you have something in elemental form, its oxidation number is 0. Here we've got elemental sodium, oxygen. You can have subscripts because diatomic oxygen is like the normal way that oxygen is in nature. P4, that's another common representation for phosphorus, arsenic, and zinc. So these would all have oxidation numbers of 0s, and typically we put the oxidation numbers above the substance, okay? You cannot have charges on the elemental form, okay? Subscripts are allowed, not charges. Okay, now if we're taking a look at monoatomic ions, this is different. Monoatomic ions have oxidation numbers that are the same as the charge. So here, they've listed a bunch of monoatomic ions. So that means for the potassium ion, +1 would be its oxidation number, which is the same as its charge. If I'm looking at the chloride ion, which is a -1 charge, the oxidation number would also be the same as its charge, which is -1. Okay? Oxygen. Oxygen is -2. Same as the charge on the periodic table, which makes it easy to remember. The exception is peroxide. Peroxide is technically a polyatomic ion. It's O subscript 2 with a -2 charge. So this -1 is actually the oxidation number for peroxide. How do you know when you have peroxide? Generally speaking, if you have a metal with an O2 in the formula, then you should be suspicious that it's peroxide. Let me give you an example. Here I've got sodium. Sodium is a metal. Do you see how sodium is with an O2? Okay, so here's where you should be suspicious. Assign the metal its normal oxidation number first. So alkali metals typically have an oxidation number that's the same as their charge, which is a +1. That's why you would want to write a +1 on the sodium. I just don't have room to write it above, so I'm writing it below. If I've got 2 sodiums in the formula and 2 oxygens in the formula, then my oxidation number for oxygen would have to be a -1 because oxidation numbers add up to 0 in neutral compounds. That confirms that this is peroxide. Okay? If I'm looking at OF2, OF2 is the other exception. If you have oxygen with fluorine, then it's a +2. Okay? All right. And to finish this off right here, alkaline earth metals also have an oxidation number that's the same as their charge, which is a +2. And then any of the other metals that have assigned charges, like the ones that are in that triangle in the transition metal region, aluminum +3, zinc +2, silver +1. You know what I'm talking about? Okay. Now, hydrogen. Hydrogen is +1. The only exception is if it's with a metal. So if you have something like calcium hydride, calcium is a metal. So calcium would be +2 because it's an alkaline earth metal. That makes hydrogen a -1 because you have 2 of them, and this all has to add up to 0, which it does. Okay? If we're talking about oxidation numbers in neutral compounds, they have to add up to 0. So if I'm looking over here at CuCl2, Cl is a halogen. Generally speaking, it's okay to assign halogen an oxidation number of -1, which is the same as its charge. Copper, we're going to determine, if I've got 2 chlorines and a -1, then copper must be a +2 for its oxidation number. Okay? If you have polyatomic ions, oxidation numbers for polyatomic ions add up to the charge on the polyatomic ion. So if I have ClO4 -1, you assign what you know. You know oxygen is a -2. We don't know what chlorine is, okay, so we calculate it. It will add up to this -1 charge on that polyatomic ion. So you've got chlorine plus 4 oxygens at a -2 add up to the -1 charge on the polyatomic ion. So this is Cl minus 8 is -1. Cl is going to be a +7, okay? Now, if I have multiple things in a compound and I kind of don't know what to assign the more electronegative element its typical charge, and we will use that as its oxidation number. So in PF5, fluorine is more electronegative than phosphorus. Assign fluorine its usual charge, which is a -1. Calculate P from there. So that would make P a +5. That would add up to 0. Last thing, if you've got something that has more than 2 elements, then the element that is written furthest to the right takes its most common oxidation number. So if I'm looking at SCN -1, N is usually a -3. So assign it a -3, then look at S and C. The more electronegative element between S and C is S. Assign S its usual charge, which is a -2. Then we can calculate carbon. So this is going to be -2 for sulfur, plus a carbon, plus a -3 for nitrogen. And since this polyatomic ion has a -1 charge, all of those add up to -1, okay? -2 and -3 is -5. Throw that on the other side. Carbon's a +4. Capiche? Awesome. Let's go to the next page. Do you feel like you need practice with this, or can I go and talk about stuff? We need practice or no? No. Okay. So I'm going to skip the practice problems. You can always scan that QR code with your phone if you want to do those to get the answers, okay? Okay, let's come down here. A decrease in oxidation number is called a reduction. So you're typically reading this from left to right. And then an increase in oxidation number is typically called an oxidation. So if you take a look at the reaction that they've given you down here, and this is just a very simple example, and I have seen stuff like this on the AP exam. This is neutral iron. right? Neutral iron would have, or elemental iron would have an oxidation number of 0. This is a monoatomic ion. It would be +2. This is a monoatomic ion. It's +2. This is elemental copper. This would be 0. Read it from left to right. If I'm going from 0 to +2, isn't that a loss of electrons because my oxidation number increased? So that means that this is oxidized, okay? And then as you're going from this +2 to 0, we are gaining electrons. And when you gain electrons, it's reduced. So this is reduced. Yeah? Then there's oxidizing agent and reducing agent. Once you label the reactants as being oxidized or reduced, then you can label it as being the reducing agent or the oxidizing agent. So whatever is oxidized, that would be the reducing agent. And whatever is reduced, that would be the oxidizing agent. Yes? Yes. Okay. Use Leo the lion goes grr. I believe it's on the next page. Okay, the Leo the lion goes grr is a really great mnemonic to help you remember oxidation and reduction. Can I go to the next page? Yes. Yes? Okay. Okay, so here it is right here, right? Loss of electrons is oxidation, gain of electrons is reduction. So when you're gaining electrons, your oxidation number goes down. Okay, all right. I'm going to go on to, now you already know this. I'm good with this. Let's go to this page. Let's take a look at these practice problems. I don't want to do all of them. I'd like to do number 2 and number 4. Okay? Enough time. So let's take a look at number 2. What's the oxidation number for strontium? 0. How about in FeBr3, what would bromine be? -1. Fe would be +3. Okay, we ignore the coefficients. That's the biggest mistake people make. This is elemental iron. It's 0. Bromine over here is -1 because it's a halogen. Strontium would be +2. That makes sense because strontium is an alkaline earth metal. Okay, as you read this from left to right, strontium goes from a 0 to a +2, gaining or losing electrons. Yeah, so this is a loss of electrons. So that means that strontium is oxidized. Be careful how you indicate what is oxidized and what is reduced. This is neutral strontium. We also have strontium ion over here in this ionic compound. Does that make sense? So that means that strontium, the neutral solid, is oxidized. And then we ignore the bromine because they stay the same. This iron is changing, +3 down to 0. This is gaining electrons. So that means you have to be really specific if it's ionic. You have to tell me the ion in the ionic compound that is being reduced. So Fe +3 is reduced. If you said Fe is reduced, you would be wrong. You would be implying that that is reduced. Okay? And then since this is oxidized, this is the reducing agent, and then this would be the oxidizing agent. We good?
Isn't it just the ion that's the oxidizing agent?
Yeah. Okay. Now for number 4 is kind of tricky because we only have one reactant. So if you take a look here, we've got hydrogen is a +1, and that means phosphorus is a -3. And then P4 is your elemental phosphorus, so it's 0. Hydrogen, elemental, 0. So P goes from a -3 to a 0. So are we gaining or losing? Losing. So this is a loss of electrons. So that means that pH3, because this is not ionic, you would say that the entire molecule is being oxidized. So pH3 is oxidized. And then H goes from +1 to 0. So that means this is gaining electrons. So that means pH3 is also reduced. Does that make sense? So that means it's also the reducing agent and the oxidizing agent together. Yeah? That's the end of 7.1. Okay, 7.2.